Swayam Prabha. Digital India. Educated India.
Okay, in the last lecture we have seen a boundary value problem using the formal finite element procedure in conjunction with Rayleigh-Ridge method and also Galerkin method, and the general steps involved in finite element procedure are first discretization of the problem domain and derivation of element equations, and then assembly of global equations. After that introduction of essential boundary conditions, and then solution of global equations for the nodal values or nodal parameters, and then substituting these nodal values or nodal parameters into each of the element equations. You can calculate at element level what are the solutions, at element level. So this is general finite element procedure, and we have seen whatever we have seen so far is all mathematical examples. We have taken a boundary value problem, the physical phenomena of which we are not aware of. So it is time for us to start looking at some physical applications. So for that I have taken simple example, axial deformation of a bar, and here for generality the cross sectional area of bar is taken to be varying, and as indicated in the figure the x axis is measured from the right side. At x is equal to 0 will be equal to 0, at at x is equal to 0 will be 0 at left side, and x is equal to L at the right side. At right side there is a point load applied F, and a distributed load is over the entire length of the bar, and the material property and cross sectional areas are also assumed to be a function of x. So this is all for general case. If you have a specific case of a bar which is having uniform cross sectional area and material properties are constant over the entire length of the bar, then you can easily incorporate those kind of things into the equations that we are going to derive. And we need to now, if you want to apply finite element method, what you need to do is you need to explain this physical phenomena, that is axial deformation of a bar in terms of a mathematical equation. That is what we require to solve using finite element method in conjunction with variational method or Galerkin method. So here what we will do is to derive the governing differential equation for explaining the physical phenomena of axial deformation of a bar. The first step is you just take a small differential element out of this bar and indicate all the forces that are acting on that differential element, and then sum up the forces in the x direction. You want this this differential element dx to be in equilibrium, that means sum of all forces in x direction, because this is a 1D problem, you have only in the x direction. Sum of all forces in the x direction equal to 0, you apply that condition, that gives us this equation, which we can rearrange, that is f and f as a function of x cancels with minus f as a function of x, and will be left with this one after rearrangement. And we know that force is nothing but it is for 1D problem, it is stress times cross sectional area, and stress is equal to strain times Young's modulus, and strain is equal to derivative of displacement. This is all what you have learned from your mechanics of materials. So we will apply all those conditions here. So if sigma x is the axial stress in the bar, then force Fx is going to be sigma times cross sectional area, everything is for generality, everything is assumed to be function of x. So according to the stress strain law, sigma stress is equal to Young's modulus times strain, and here is capital E is Young's modulus and epsilon is axial strain, again all are functions of x. So substituting all these quantities, the given or the whatever equation that we obtained earlier, that can be rewritten, that is replacing f with E times area of cross section times derivative of u with respect to x. So that is what is done here. So this is the governing differential equation explaining the phenomena of axial deformation of a bar, and this is valid over the length x going from 0 to L, because that is the region we have taken for derivation of this differential equation. And now if you see, this is a second order differential equation, and you require two boundary conditions to solve this equation. So the two boundary conditions, we need to look at the problem, that is the problem that we are already looking at, and we need to write the corresponding boundary conditions. So the first boundary condition is, I mentioned to you, the bar is fixed at the left side, that is at x is equal to 0, displacement is equal to 0, that is the first boundary condition. At x is equal to 0, u is equal to u evaluated at x is equal to 0 is 0, and a point load is applied, a point load of magnitude f is applied at x is equal to L. You just learned that f is nothing but area of cross section times Young's modulus times derivative of u with respect to x. All these quantities we need to evaluate at x is equal to L, in case they are all functions of x. So when all these quantities, that is E times A times du dx, all are evaluated at x is equal to L, they must be equal to the f, the point load that is applied. So this is the other boundary condition. So looking at the physics of the problem, we have written the two boundary condition. One is u evaluated at x is equal to 0 is 0, the other boundary condition is the point load applied at x is equal to L is equal to the value f. So if you look at these two boundary conditions, you can easily recognize one of them is essential, the other one is natural boundary condition, from the thumb rule that I already mentioned to you in the earlier lectures. That is, if you have a boundary value problem of order 2p, those boundary conditions of order 0 to p minus 1 are essential boundary conditions, and those boundary conditions of order p to 2p minus 1 are natural boundary conditions. And also if you see the physics of the problem, u evaluated at x is equal to 0 is it is essential, otherwise if this boundary condition is not satisfied, then it is not, in fact it is not a bar problem. So it is in fact it is essential that this boundary condition you need to satisfy, whereas the other boundary condition, even if a force F is not applied at the right tip, then still a bar will be there. So that is why it is called natural boundary condition. So now we have the physics of the problem, the physical phenomenon is already expressed in terms of differential equation, and that is where we can start our knowledge that we gained already from the previous lectures, that is either we can use variational method or Galerkin method, and we can substitute finite element approximations into it and solve for the unknown quantities. So here now we can write following the, here what I mentioned, u evaluated at x is equal to 0 is 0, that is essential, and the other boundary condition is natural boundary condition. And now we can use our knowledge in variational method, Rayleigh-Ridge method, and we can write directly the equivalent variational functional for this problem. And that is you need to take the given differential equation. If you want to follow variational procedure, you just recall the steps involved, take the differential, given the differential equation, multiply with variation of the quantity that you are looking for, that is variation of u, and integrate over the problem domain. equate it to 0, and then the next step is apply integration by parts, reduce the higher order derivative terms, and then you need to substitute the condition that variation of u wherever essential boundary condition is prescribed, at that point variation of u is equal to 0, and also at this point you can also substitute any natural boundary condition that is given, and then simplify it and bring it use variational identities and bring it into the form variation of some quantity is equal to 0, and whatever is there inside the bracket is what is called variational functional or equivalent variational functional. And it turns out for this problem, that is axial deformation of a bar, this variational functional is nothing but potential energy, and that is why here it is denoted using capital pi. And if you are good in writing directly the potential energy equation for or potential energy expression for a structural system, you can directly write it here. Potential energy is nothing but strain energy minus work done by the applied forces, and if you look at this potential energy equation, the first term is nothing but strain energy. If you recall from your mechanics of material, for a bar problem, bar under axial deformation, strain energy is nothing but sigma square over 2E times volume, and because if all are constant, that is area of cross section is constant, and if Young's modulus is constant, if sigma is also constant, you can apply this condition, but here all are assumed to be varying over the cross sectional entire length of the bar. So it is given as in the here in the equation, that is strain energy is equal to integral 0 to L half E times A u prime square, that is nothing but derivative of u with respect to x. If you can easily show whatever is there, half E times A u prime square is nothing but sigma square over 2E times volume, sorry, a times dx is volume, and half times E u prime square is what is sigma square over E. So if you integrate over the volume, you will get the entire strain energy. And if you recall what is work done by the applied forces, it is nothing but force times displacement. Since q is distributed load, so it is we need to use integral 0 to L. Q is a function of x, even though it is not explicitly written there. Q times u gives you the force, and you need to integrate over the entire length of the bar. F is a point load, and the displacement evaluated at x is equal to L. F times displacement evaluated at x is equal to L gives you what is the work done by the due to the application of load F. So if you are good at writing potential energy expression directly, you can do it, or you can go start with the given differential equation and apply the whatever procedure we learned for variational method or Gralich-Ridge method, follow that procedure, and finally you will arrive at this equivalent variational functional. So now we are ready to substitute. If we know finite element approximation, now we can substitute finite element approximation of u and apply the stationarity conditions that we already did in the last class, and get the element equations for this problem. So now the finite element equations can be derived, either you can use Galerkin method or variational method, and here a typical element is shown, and here this element for this element at the nodes 1 and 2 point forces are shown F1 and F2, and also the sign convention, please see the forces are positive in the direction in which x is positive, and the nodal coordinate of node 1 is x1, nodal coordinate of node 2 is x2, and q is the distributed load that is acting, and Ea is constant. The degrees of freedom associated with node 1 is u1, degree of freedom associated with node 2 is u2, and length of this typical element is L. So, now if you see this element, actually you have 2 point loads applied. So, if you want to write potential energy functional or equivalent variational functional, it looks like this. Additional if you see, if you compare this equation with the previous equation that you got for the bar which is fixed at one end, you have only one f times u there, one f times u term there, whereas here you have f1 times u1, f2 times u2, because you have point loads applied at the both ends at 1 and 2. Because of that reason you have f1 u1, f2 u2, 2 terms are there, and the rest of the portion is similar to what you already have. So, now what we can do is we can this x1 x2 coordinate system we can map into s coordinate system, or x coordinate system can be mapped into s coordinate system such a way that x1 coincides with s is equal to -1, x2 coincides with s is equal to 1. So, in the last class we have seen what is the relation between such kind of mapping between x coordinate system and s coordinate system, which you can obtain easily using linear interpolation, or there is a similarity between that relation and equation of the straight line. I already explained all these things in the last lecture. So, now applying those things, you get the relation between s coordinate system and x coordinate system. Once again, s coordinate system is defined such a way that s is equal to -1 coincides with x1, s is equal to 1 coincides with x2. So, the relation between x coordinate system and s coordinate system is this. The advantage of doing this kind of mapping is the limits of integration now becomes -1 to 1 instead of x1 to x2. So, we can easily apply Gaussian quadrature, and now using this relation we can manipulate and get the inverse relation between x coordinate system and s coordinate system, and also we can take derivative on both sides, we get these relations. And now we need to write a trial solution in terms of s coordinate system. So, now the entire problem we are going to work in s coordinate system. So, trial solution is u is equal to n1 u1 plus n2 u2, and the shape functions n1 n2 are already explained these things in the last class. N1 is equal to -1 1 minus s over 2, n2 is equal to 1 plus s over 2, and this can be compactly written, the trial solution can be compactly written as n transpose d, and from there it follows what is u prime. U prime is nothing but derivative of u with respect to x. Using chain rule you can write derivative of u with respect to s, derivative of s with respect to x. You know what is the relation between derivative of or relation between s and x coordinate system. So, you can write what is a ds over dx, ds over dx turns out to be 2 over L, and du over ds you can use the first equation and get what is du over ds. So, u prime turns out to be what is that b transpose d, where b transpose is defined as 2 over L minus half. So, that is what is defined as b transpose, and please note that this notation is only applicable or is applicable for all the later lectures in this course, and the notation depends on the author. Each author will have a different way of using different notations. So, you should be careful when you are referring various textbooks. And now what is derivative of shape function with respect to x, what is derivative of shape function n1 with respect to x, shape function n2 with respect to x, that you can easily write it from the earlier your knowledge. We have seen n1 is equal to x2 minus x over L, that is n1, and so you take derivative of it, you will get minus 1 over L. N2 is nothing but minus x1 plus x over L, and if you take derivative of it, you will get 1 over L. And if you sum up these derivatives of n1 n2, it turns out to be 0, and also shape functions, that is n1 plus n2 is equal to 1, that is sum of shape functions is equal to 1 and derivative of shape functions is equal to 0. This is valid at any point in the domain, and these are called consistency conditions. And now you got trial solution, and what is the derivative u prime, derivative of u with respect to x. So now if you see our potential energy equation, we have u prime square, and please note that u prime is a scalar quantity. So u prime square, I can write it as u prime transpose u prime. If you have a scalar quantity, scalar square of a scalar quantity can be written as transpose of that scalar quantity times that scalar quantity. So using that reason, u prime square is written as u prime transpose times u prime, and you know what is u prime, it is b transpose d, and substituting all those quantities you get u prime square as given here. And now you got u prime square, so you substitute u prime square, and also you can substitute what is u is n transpose d, and finally the given functional can be written in terms of finite element approximation in this manner, which you can further simplify. So the first integral inside whatever is there, first integral, if you see the first integral term can be rewritten in this manner, and please note that u1 u2 are nodal values or nodal parameters, so they are not functions of the coordinate system. So you can pull them out of the integral, and whatever is left inside the integral, that is half is also constant, you can pull out of that, pull that also out of the integral. Whatever is function of x, E is a function of x or s, A is function of s, L square, 1 minus 1 minus 1 1 times L over 2 ds, that is what is defined as k, and if you carry out integration you get this one, E A over L 1 minus 1 minus 1 1, and this E A, while carrying out this integration, it is assumed E A are constant, so we can take them out of the integral. So whatever is given here, k is equal to E A over L 1 minus 1 minus 1 1, that is applicable only when Young's modulus and cross sectional area are constant, and that is a specific case, and if you have a general case you need to integrate them, putting them inside the integral, and k is defined like this. RQ is defined like this, the second term is defined as RQ, and here if you see the second term actually it has n transpose d, d is taken out, d consists of u1 u2, it is taken out of the integral, and whatever is remaining, that is defined as RQ, and we can carry out the integration, and finally we will get QL over 2 QL over 2. And if you see last two terms, you have F1 u1 times F2 u2, F1 u1 and F2 u2, these terms are there, the last terms, and in that you can again put them in the form of this vector F1 F2 times d vector. So r beta is defined like this. So once we define k r q r beta, we can write the potential energy in a compact form like this. And now you can see potential energy is a function of u1 u2, and the requirement is variation of potential energy should be equal to 0, or the other condition is you can variation of potential energy is equal to 0 is satisfied when partial derivative of potential energy with respect to each of the nodal unknowns or nodal values is equal to 0, that is partial derivative of pi with respect to u1 is equal to 0, partial derivative of pi with respect to u2 is equal to 0. You get two equations. This is the first equation applying the first condition and the second condition. As you can see here, whatever the procedures you have learnt, we are now applying to a physical problem. You can see the applications of those things, that is stationarity conditions. And now you got two equations. These two equations are looking similar, so we can put these two equations in a matrix form. In this manner, and if you see 1 0 0 1 is identity matrix. So, whatever you multiply with the identity matrix you get the same thing. So, this can be compactly written. K value is substituted, K is equal to E A over L 1 minus 1 minus 1 1, that is what K, and R beta and RQ values. RQ is nothing but QL over 2 QL over 2, R beta is F1 F2. And if you see this equation, and the first matrix is what is called stiffness matrix, U1 U2 is displacement vector, and whatever you have on the right hand side they are all related to forces, and if there is no body force or distributed force Q, then that vector is going to be 0, and if you have only point forces then you will have only F1 F2. And you solving that equation system you can get what is U1 U2. Once you get that is for one element, you need to assemble such kind of equations for all elements in the system and assemble the global equation system and apply the boundary condition, essential boundary condition, solve for the global equation system. Once you get the nodal values, you can go back to each element and then find strain in each element. Strain is given by B transpose D. Strain is nothing but derivative of u with respect to x. You already know what is derivative of u with respect to x, B transpose D. B transpose is defined as 2 over L minus half times D. D is nothing but u1 u2. So, strain you can obtain using this equation. Once you solve for u1 u2, once you know the values of u1 u2, you can calculate the strain in the element using this relation, and once you know the strain you can find what is stress and axial force. And now we will take an example and apply whatever we learned till now related to the axial deformation of a bar. So, let us take a stepped bar like this, which is having different cross sectional areas over its length, and the cross sectional areas, the value of cross sectional areas and also the lengths over which those cross sectional areas are valid, and also the material property and the load applied, everything is given here. And since bar is having different cross sections, at a particular point we will take element 1 or node 1 coinciding with the lower end, node 2 coinciding at the point at the location at which the cross sectional areas are changing, and node 3 is at the point where load is applied. And let us call the element connecting nodes 1 and 2 as one element, first element, and element connecting nodes 2 and 3 as second element, which is indicated as 2 there in the figure, and also the cross sectional areas are indicated for clarity there. So, now you have element 1 and element 2, you know what is Young's modulus, cross sectional area, length of element 1. So, you can easily assemble what is the stiffness matrix of element 1 or elemental equation system you can assemble. And element 1, if you look, no load is applied in the region of element 1, and if you look at element 2, all the material properties and cross sectional areas, all the geometrical details and material property details are known to you, EAL, and also the load that is applied is known. So, you can easily assemble the elemental equations for element 1, noting down the geometrical properties, material properties, length of that element, we can substitute into this equation that we just derived. And please note that the equation system that we derived is applicable only when cross sectional area Young's modulus are constant throughout the entire cross section, entire length of the area of cross section, and Young's modulus are constant over the entire length of the element. Since the element that we are looking at is having same Young's modulus and cross sectional area, we can apply these equations, element equations, substituting the corresponding values for this element, we get this equation, element equation. Superscript here is denoting the element for which it is, this equation system is for. Okay. So, now we can also write equations for element 2, and simplification of this gives you this equations for element 2. Again note down cross sectional area, Young's modulus, length, substitute into the element equations. Again superscript is denoting the element number for which this equation system is applicable. And if you know see the difference, please note that F is applied, F2 here is taken to be equal to 1, because force 1 of 1 kilogram, not load, not force, load of 1 kilogram is applied at node 3, and the positive x direction, our positive x direction is going from the fixed end to the top. So, the load is acting in the same direction as the positive direction. So, it is taken as 1, and we get the equation system for element 2, which upon simplification gives you this one. So, now you got elemental equations for element 1, elemental equations for element 2. So, now you are ready to assemble the global equation system. Assembly of element equations, and please note that this problem is a one dimensional problem, and there are 3 degrees of freedom, one at each node. So, you will have a global equation system of size 3 by 3, and the element 1 contribution goes into the location 1 and 2, because the element 1 is connecting nodes 1 and 2. Element 2 contribution goes into the locations 2 and 3, because element 2 is connecting nodes 2 and 3. So, that is what is substituted, and this is the global equation system. Similarly, the force vector from element 1 goes into the 1 and 2 locations of the global force vector, and also from element 2 the contribution goes into 2 and 3 locations of the global force vector. And now after substituting all this, we get this global equation system. Now we are ready to apply the essential boundary condition. Essential boundary condition is u evaluated that x is equal to 0 is 0, that is bottom edge is fixed, that is u1 is equal to 0. So that is substituted, u1 is equal to 0 is substituted, and please note that wherever you apply displacement boundary condition, wherever you apply displacement boundary condition, reaction will be developed. So that is one of the important thing that you need to note down. It is not that because u is 0, that is here u1 is 0, it is not because of that reaction is developed. U1 you can take any value, reaction will be developed. So since displacement is equal to 0 at node 1, reaction R1 is assumed to be developed at node 1, and this equation system, what you can do is you can use partitioning of matrices and solve for unknowns u2, u3, and then back substitute those unknowns into the first equation and get back calculate what is reaction R1. Or you can actually multiply or you can actually eliminate the first row of the equation system and you can get this one. And if you do multiplication of this, on the left hand side, it reduces to this one. If you compare, this is what is called reduced equation system. If you compare reduced equation system with the equation system that you have without applying the essential boundary conditions, what we basically did is wherever essential boundary condition is applied, remove that particular row and column in the global equation system, then we can get the reduced equation system directly. So now we can solve this 2 by 2 equation system for u2, u3, we get this u2, u3, and once we get this u2, u3, what we can do is how do you check whether these u2, u3 values are correct or not? What you can do is you can go back and calculate what is R1 reaction, and you know that for a body to be in equilibrium, the sum of all forces should be equal to 0. So substitute this reaction into the free in the free body diagram and see whether forces balances or not. Actually, in fact, here the reaction is having same magnitude as the load that is applied. 1 kilogram is applied, so R1 came out to be -1 because it has to balance the positive 1, so it is -1. So we got what is u2, u3. So what we can do is, and u1 is equal to 0, using these nodal displacement values, we can go to each element, element 1, we can calculate what is strain, stress, again element 2, strain and stress. If you further want what is the load or what is the load in each axial force in each of the elements, you multiply the stress value with cross sectional area of each element, you get the what is the force carried by each part of the that bar. So now we solved a problem, we have seen a physical applications of the techniques that you learnt. So now we have seen a structural mechanics problem, that is axial deformation of a bar, and now let us see what is the physical interpretation of this element equations. For axial deformation element shown, suppose we apply forces at nodes such that they produce u1 is equal to 1, u2 is equal to 1. You have the axial deformation of bar, the equations system is there with you, that is E A over L 1 minus 1 minus 1 1 times u1 u2 vector is equal to QL over 2 QL over 2 plus F1 F2 vector. You have this equation system with you. So, in that equation system, let us denote the force at node 1 as K11, force at node 1 for unit displacement at node 1 and 0 at the other, and at the other node 2 by K21, force at node 2 for unit displacement at node 1 and 0 at the other. So, what is basically done is, in the equation system that you already derived, u1 is taken to be 1, u2 is taken to be 0, and instead of F1 F2, ignoring distributed load, the force vector consists of only F1 F2. F1 is denoted as K11, F2 is denoted as K21. Okay. So, this is the equation system you have, and now you multiply on the left hand side. If you multiply, if you carry out multiplication on the left hand side, that is E A over L 1 minus 1 minus 1 1 times vector 1 0, it turns out that K11 is equal to E A over L, K21 is equal to minus E A over L. If you see K11 value, K21 value, that is nothing but first column of K matrix. Okay. So, now what I will do is, I will take the same equation system, except that u1 will substitute u1 is equal to 0, u2 is equal to 1, and let us say corresponding forces, let them be denoted using K21 and K22. Okay. Similarly, forces for producing u1 is equal to 0, u2 is equal to 1, and if you carry out the multiplication, it turns out that K12, K22 are nothing but, whatever values you get are nothing but second column of matrix K. So, what we can learn from here, column I of stiffness matrix can be obtained by computing forces required to give unit value to degree of freedom at node I, while keeping other degrees of freedom is equal to 0. So, and we can generalize this to a n by n equation system, where ijth component of stiffness matrix is nothing but force at a degree of freedom I due to unit value of degree of freedom j, or unit value of displacement at j while keeping other displacements equal to 0. So, that is what each component of stiffness matrix is. So, this is a physical interpretation of element equations. And now, let me ask you, we have taken a bar under axial deformation, and here we have derived the element equations. but if I replace that bar with a spring having spring constant, how the equation system looks like. Please note that if you see the equation system of the elemental equation system for a bar under axial deformation that we just derived, K is E A over L, stiffness matrix is E A over L, 1 minus 1 minus 1 1. In that E A over L is what is the stiffness is like a stiffness of a spring, stiffness constant of a spring. So, what we can do is, if you want finite element equation of a spring, we can easily write it as K times 1 minus 1 minus 1 1 times u1 u2 vector is equal to f1 f2 vector. And how this spring looks, this is the spring, nodes 1 and 2 are defined, and spring constants we need to know spring constant. So, if you want to replace a bar element with a spring element, what you need to do is you need to find a spring having spring constant is equal to E times A over L of bar element. So, this is a spring element. So, now you learnt what is a bar element and what is a spring element. Now, let us see this example. Find axial forces in spring bar assembly shown in the figure, and here units are given in FPS units and corresponding SI units are given in the brackets. And since FPS units are looking in a more without any decimals, much decimal points, so the decimal places will work in FPS units. So, all the values are given here, spring constant, length of the bar elements, the steel and aluminum, and force that is applied, Young's modulus, cross sectional areas, all are given here, and a figure is also shown with all the degrees of freedom u1, u2, u3. Please note that u1 and u3 are fixed, that is u1 u3 values will be equal to 0, they are the essential boundary condition, and the natural boundary condition is force F applied on the rigid bar is equal to 15,000 pounds, and here the force F is applied in the middle of the rigid bar. When you are assembling the elemental equation system, this F you can when you are assembling this spring element, you can actually put it for contribution for spring element or steel or aluminum bar, but it is acting at this node 2. So, that is what you are going to see here. Equations for spring element stiffness matrix is K times 1 minus 1 minus 1 1. So, you find what is the spring constant for spring element, substitute that, you get this equation system. Here if you see spring element at node 2, this force 15,000 pounds is acting, that is why this is shown as a contribution to the spring element. And for steel bar element equation system, you know what is Young's modulus of steel, it is given area of cross section of steel bar, length of steel bar. So, using that information you can find stiffness matrix, and the force here this is what I mentioned, the force is actually the force contribution is added to the spring element, that is why it is not shown here for steel bar element. Similarly, equations for aluminum bar element can also be assembled, taking the value of cross sectional area of aluminum bar, Young's modulus of aluminum bar and length of aluminum bar. So, now you have the elemental equations for all the 3 kinds of components here. So, now you are ready to assemble the global equation system. Spring contribution goes into rows 1 and 2, rows and columns 1 and 2, and steel bar element contribution goes into the location 2 and 3, and aluminum bar contribution also go into location 2 and 3, and the force is applied at node 2. So, that is what is shown there, and u1 is equal to 0, u2 is u1 is equal to 0 and u3 is equal to 0. So, what you can do is you can eliminate rows and columns corresponding to the degrees of freedom which are equal to 0, that is eliminate rows and columns 1 and 3. So, you will be left with one equation, one unknown, and you can solve for u2. And while we did all this, what we did is note that applied load at node 2 was arbitrarily assigned to node 2 of spring element, this is what I mentioned. However, this does not mean that all this load is taken up by spring element. It can be assigned to either steel or aluminum bar. The only thing that is important is it should appear in the global equations corresponding to u2. So, this is what we have done. So, applying the essential boundary conditions, u1 is equal to 0, u3 is equal to 0, the global equations incorporating these boundary conditions becomes this, and reduced equation system you will have only one unknown u2, which can be obtained solving the second equations, which gives u2 is equal to this. And now you know what is u2, you can calculate the reactions R1 and R3. Please note that if you sum up all the forces, that is force applied 15,000 pounds and plus R1 plus R3 should be equal to 0 for force equilibrium. So, now you got all the nodal displacement values, you can calculate the forces. Once displacements are known, strains and stresses can be calculated using element equations. First one is spring force. Spring force is what? u1 is already 0, u2 is what you just found. So, spring force is going to be stiffness times u2, it gives you the spring force. Both FPS units corresponding SI units are shown, and also as expected it turns out this value is positive. Positive means tension, negative means compression, that is our sign convention. So, positive means tension. So, it actually makes sense because the force is trying to pull the spring. And what is the strain in steel bar? Stress in steel bar, and here strain is negative. Negative means stress whatever value is calculated, that is compression, axial force is compression. Similarly, aluminum bar strain, stress, here negative sign is missing, sorry about it, and this is expected, that is steel bar and aluminum bar will be in compression, and spring will be in tension, because force is acting from the left side towards right side. Since the spring is towards right and the aluminum and steel bars are towards left, aluminum bar and steel bar will be in compression, whereas spring will be in tension. Okay, we will continue in the next class.